Today's guest is Professor Rajat Manohar, who is a professor of electrical computer engineering and a Stephen H. Weiss Presidential Fellow at Cornell Tech. Professor Manohar has won 5 awards for his teaching, 7 Best Paper Awards for his research, and he was named to MIT Technology Review's Top 35 Young Innovators Under 35 for his contributions to low-power microprocessor design. He's a worldwide leader in asynchronous design. We're going to hear more about that today. And in addition to his research and teaching, he serves as Associate Dean for Research at Cornell Tech. So first of all, Rajat, thanks for joining us.
Thanks for having me.
So you used to be here on the Ithaca campus. Actually, we have an office that's right across from each other. We're colleagues here in the Computer Systems Lab. But now you're at Cornell Tech in New York City, which is kind of new for Cornell. So can you explain what Cornell Tech is all about and how it differs from Cornell at Ithaca?
Sure. So Cornell Tech is essentially a new graduate campus that Cornell started in New York City. And this graduate campus is focused on master's and PhD education. And as the name suggests, I mean, it's about tech, the tech sector. And so sort of the core disciplinary areas are sort of computer science, information science, operations research, electrical and computer engineering, but also business and law, right? So all the things that intersect the technology sector. In some ways, you know, it's funny. I always wonder, you know, what's really different about Cornell Tech? I mean, because after all, we have faculty at Cornell Tech who come from, you know, other campuses.
Right, like you, for instance.
Like me, for example, and other people we've hired have come from other universities and so on and so forth, but they were always at a regular university. So what's really different? Well, one way to think about it is, you know, Cornell Tech, one of the things Cornell Tech cares about a lot is this idea of external engagement, as in, you know, faculty doing research that sort of engage with the non-academic community. And that could be, you know, they're interested in, say, you know, education at the K through 12 level, or, you know, they started a company that commercialized some technology that came out of their lab, or they worked with, you know, a large existing company to take some of their ideas and see them sort of deployed in real products, or, you know, maybe influence government policy in some way. So, you know, essentially having a research profile where you also are interested in the non-academic recognition and impact of your work. And, you know, these faculty, as you know, exist at many, many campuses, right? Everybody has these faculty. And at Cornell Tech, we're sort of trying to collect them all.
I see.
So that's sort of a requirement for all faculty. I mean, this is not a requirement on any other campus. Different faculty have different interests, and they do what they, you know, which makes sense. But at Cornell Tech, we sort of require everybody to have this part as part of their research portfolio, right? In addition to the regular things you do, you have to have this as well. So so one way to think about it is there's an extra that everybody expects to have here for all the faculty, but in addition, you know, it's also focused in terms of just the technology disciplines, right? So there's a focus and there's a mission of having this sort of external engagement piece. And, you know, it's really consistent with Cornell, right? I mean, Cornell started as a land-grant university.
Right.
Which, you know, the agriculture school, for example, has a huge impact on, you know, farmers and things of that nature. And this is sort of the equivalent on the tech side, that we're sort of saying we have to do this as well, right? So that's basically the difference. So it's sort of complementary to the campus. You know, a faculty member who we hire here, we would probably be happy to hire in Ithaca as well. After all, we still have all the departments are still unified. So everybody, you know, has the same hiring criteria. But this is something there's an extra dimension that we expect every faculty member to have.
And right now you're Cornell Tech's only been around for a pretty short period of time, right?
Around 2.5 years.
2.5 years, so it's kind of building up, but eventually there's a plan for a permanent campus on Roosevelt Island.
Exactly, right. So that actually, if there hadn't been the snowstorm, the snowstorm that didn't really happen, we would have actually been at the groundbreaking earlier today, but that all had to be postponed because of the snowstorm. But yeah, I mean, so they finished demolishing the site, and now they're beginning to start the construction. So that's underway, and we plan to move there summer of 2017 is the move-in date.
And that'll be like the first building, and then it's going to build up from there over a number of years.
Right. We should have, I think.
Well, first couple of buildings, perhaps.
A couple of buildings, yeah, it should be up. But I think 3 buildings should be up for sure by then. So the first phase of campus. Yeah, that's exciting.
So I want to move on to talk about your own personal story. I'm asking everybody about their own careers and hearing about their story, about how they got to where they are today. So first of all, when you were in high school, what inspired you to pursue engineering? And did you think you wanted to do electrical engineering at the time, or did you just decide you wanted to do engineering?
I don't think to be honest, I don't think knew I wanted to do engineering in high school at all. I mean, nobody ever told me what engineering even was in high school. I mean, I was taking physics and math and things like that, and chemistry and all the usual stuff. And probably the thing that got me interested was some books I read when I was in high school. So my brother's a physicist, and he gave me some books to read because he thought I'd be interested in them, and they had to do with sort of computing in general, and I found that very interesting. And so, when I got to college, I took classes related to that, and that sort of, and then I realized, well, I really enjoyed designing things and not just studying things, right? So I mean, there's sort of those two different sides. Sometimes the difference is not that obvious, but there's a great quote from what's his name, von Karman, who it's like the father of aerospace engineering, if you want, and he basically said something to the effect that what engineers create what never was. So you're creating new things. You learn from science, but then it's much more creative. You're not just studying what's already there. You're actually creating something new. And I thought it was a very nice description of what engineering really is, and that sort of appealed to me. So that's part of why I got into that. I got degrees in things that weren't necessarily called engineering, but it turns out that's really what they were. So I got my undergraduate degree from Caltech, and essentially at the time, at least, Caltech had there's a certain number of majors in engineering, but primarily probably the largest one is called engineering and applied science, which is a very broad topic, and that's because they actually weren't offering majors in a lot of the subjects. So for example, I took all my classes in computer science, but computer science was not an undergraduate major at Caltech when I was a student there. So there were a lot of students who had interests in a number of different engineering disciplines that ended up getting degrees in engineering and applied science because Caltech is such a small place. So they weren't offering a full curriculum.
But when did you start thinking about electrical engineering as your chosen area in engineering?
So I started it. I was always interested in computing, and what ended up happening was I took a class when I was an undergraduate student that was supposed to be about computing, but it ended up being much more about how computers actually work and how they're built and designed, and that at Cornell is in electrical engineering, that was really interesting to me because it was a very one of the things that I found really interesting was this topic of parallel computing, which everybody's has become it's all the rage these days. And what was nice about chip design was everything on a chip. If you put two things next to each other on a chip, it's in parallel. So, in fact, it's an interesting scenario where parallelism is free, in some sense. And if you have to do things one after the other, that actually costs you. It's expensive to do that. And I thought that was a very interesting way to think about the world. And so that's what got me into sort of chip design, and that's sort of what I've been doing ever since. And that, of course, is electrical engineering, right?
So this first course, actually, it was kind of an introductory course, but actually talked about parallelism and how to get parallelism and the advantages of parallelism.
Right, exactly. So it was a course on, so it was sort of a sequence of courses. So there was the first set of courses on concurrency, which I really enjoyed. And the person teaching that was actually teaching the chip design course. And he was like, you should take this because you like concurrency. And I was like, okay, that doesn't make sense, but I'll do it. And he was right. And he ended up being my thesis advisor. So that's basically how that happened.
So that professor, he ended up convincing you. You decided to eventually get a PhD.
Right.
I'm not sure you had that initial idea to get a PhD, but was it from his course and from his encouragement that kind of led you to a PhD?
To some extent, yes. There were a number of, so one of the things was I ended up taking some advanced courses when I was an undergraduate, and quite a few of those courses ended up sort of right before the semester ended. Essentially, the professor would say, well, and that's kind of all we know about this topic. And everything else, we don't know yet. And that I was always very intrigued by that. I was like, oh, that's really cool. Let's try to figure out what's next. And that sort of encouragement made me, and part of that led into a research project. I was a work study student with one of the professors who taught a class that was of that nature, and then I ended up doing a research project with him, and then one thing led to another. It was kind of clear after a few months of doing that I really enjoyed it, and so applying for a PhD was the obvious next step. So that's how I got there.
Now I want to talk about your work in asynchronous design. So in this course, I teach students that we have synchronous circuits, where the circuit is advanced by a periodic clock. But you work in asynchronous circuits, and this is sometimes called clockless logic because there's actually no global clock that's sent around. They operate in a different way. So can you explain how an asynchronous circuit works and the advantages and maybe the challenges in designing circuits this way rather than as a synchronous circuit?
So sure. So in an asynchronous circuit, basically a good way to think about it is computation sort of progresses when data arrives. So instead of waiting for the clock tick to show up to say, let's do the next step, you wait for a new input value to arrive before you do the next step. So that's the basic sort of operating principle. So instead of saying, well, when the clock tick shows up, I have my new inputs and I'll produce my sort of previous outputs. Right? That's sort of the conventional way of doing things. Another way of doing this is to say, well, I'll tell you when I'm giving you a new input, so I'll have a special signal that I'm going to use to tell you a new input's arrived. And then when you produce your new output, you do the same thing. You produce a signal saying, hey, here's a new output. Right? So that's the basic difference, and that's actually a very natural way of interactions. I mean, sort of apart from sort of synchronous circuits, pretty much the rest of the world behaves this way. Right? You look at biological systems, you look at, I talk to somebody and, I hear a response based on, what I said and so on and so forth. That's a very natural way for, human beings or sort of anything to interact. And that's how most of the world works. And even in computer systems, pretty much as soon as you leave the confines of a small part of your chip, that's true as well. Right? Systems operate sort of asynchronously with respect to each other.
Now, this is even on a smartphone SoC, right? We think of those as synchronous systems, but they have asynchronous aspects to them as well.
Right, and depending on which generation of the design, there could be more or less of this in the system design itself. Another good example is sort of almost every memory today. There's a little core of it that's actually asynchronous because it turns out that there's a bit of that. Otherwise, it would be slower than it should be. You can actually go a little faster that way. So a lot of memories have this sort of asynchronous circuit built in. A lot of times it's just easier to design a system where different parts operate at different frequencies because some parts are naturally faster than others, but then they're operating with different clocks and then they need to communicate with each other, and that's also asynchronous. So those are sort of the most commonly found examples in the commercial world.
Now, this last part about you have two. I have a CPU and a memory, or even CPUs need to communicate, and they're not running off the same clock, and they need to communicate with each other, even though their clocks aren't lined up.
Right.
That's an example of asynchronous communication. But now you've done some work in this area, right? Because you have to put this through a series of D flip-flops, which delays the transfer of information between those. So you've done some work in order to make that, to improve the performance on that. Can you talk about that a little bit?
Sure. So there's a problem when actually it's sort of an interesting problem. There's essentially a fundamental problem if I need to communicate with if one part of the system needs to communicate with another part of the system, and that the part that's receiving the information is synchronous, but that synchronous operation of that system isn't related to the part of the system sending information over, right? And so what can happen is the receiver has got this clock ticking along, and the input might change sort of right around when the clock is supposed to tick, and that can create problems. It's called a metastability problem. I don't know if you talk about it in your class, but it's actually a very tricky thing to think about. In fact, it's a good example in the literature where in the initial, the 60s, people didn't even realize this was an issue. So lots of very smart people were fooled. So, it's a very tricky, subtle issue. And So typically the way you can handle this problem is, it turns out we don't know how to do this with 100% reliability. But what we know how to do is, we know that if we allow this process to take longer by having multiple D flip-flops, for example, then the failure rate goes down exponentially. So you can make the failure rate to be low enough that, you're more likely to, the power supply is more likely to break than,
So you can't guarantee no failure, but you can put enough flip-flops so that you can make it so small that it won't be an issue, typically.
So for all practical purposes, you can assume the system's reliable, right? So exactly. So the problem with that is, when I'm sending you information, I have to go through all these flip-flops, so I have to wait to receive the information. And unfortunately, the waiting is inherent. You can't get the information through reliably without waiting. But actually, what we did, which you're alluding to, is there's a way to cheat, right? And the way you cheat is, so the reliability issue only shows up when you finally need to receive the circuit, the information in the clocked domain. But I can view the entire process of transferring that information as going from an asynchronous domain to a clock domain. But what that means is, I can compute on the logic, on the data going through asynchronously before the data arrives at the destination.
So instead of just wasting these full clock cycles, you're actually doing useful computation within those clock periods.
So you can cheat. So you can hide computation into this. You can push some of the computation you need to do onto this delay. And so even though you're still waiting, you're still getting useful work done. And that has to happen in the asynchronous domain, because the asynchronous domain is ready to receive inputs whenever, because it isn't being clocked. So it can just wait until the data arrives. So that's the basic idea.
Now, you've had considerable success in designing with your students. You've designed and built and tested a large number of chips, and asynchronous chips. And I don't have time to talk about all of them, but one of them you designed was, you call it SNAP, which is an asynchronous processor for sensor networks, and that showed a huge advantage in power over a synchronous counterpart. And then another is field programmable gate arrays, or FPGAs, programmable logic, where your research led to a startup, Acronix. So can you talk about those two applications and why doing things asynchronously has an advantage over doing things synchronously?
Sure. So I'll talk about the sensor network domain, the SNAP chip that we did. And we sort of looked at this problem. It's kind of funny now to think about it, looking back at sort of late 1990s is when we started looking at this problem. And sensor networks weren't even a thing back then. But we had faculty members in ECE at Cornell who were interested in wireless communications, and they could sort of see the writing on the wall that you could build systems like sensor networks. And so there was a collaboration that came out from that, and that's why we ended up designing this processor. So that was sort of an interesting thing in itself. But what ended up happening was we looked at what people were using in the commercial world in this space at the time, and everybody was essentially trying to take sort of the desktop model and make it small, right? And the problem with that really was that the application domain had some very, very different characteristics. And the first one, which is kind of, it's the obvious one, of course, look, now it's obvious, was that actually these little sensor nodes were doing very little useful work, right? I mean, I have a temperature sensor. I mean, I'm computing sort of the running average of the temperature. I'm getting samples like, every millisecond if I'm really, really aggressive. I mean, temperatures don't change on any time scale that we worry about in electronics, right? We're worried about nanosecond time scales.
Right, and these are very, very, very long.
So, like on my phone, if I look at the temperature, it's like once an hour, right? So, I mean, that was one thing. There was actually very little work being done. And the problem was that all the conventional systems were being designed in a way that, waking up was a very expensive operation because most of the time you're busy doing useful computation. And so it was okay to have expensive wake up, and then you can do useful work. And so there was all this overhead involved in the full system on that. And so what we ended up designing was this. So in the asynchronous domain, on the other hand, I mean, normally the system is waiting for inputs. And as soon as inputs arrive, you start computing, and then you produce the output, and then we go back to waiting for inputs. And that's sort of a very natural way applications look like in the sensor network domain, right? So there's a very good match between what an application looks like in the sensor domain and then sort of how we design our circuits. So we said, well, we should be able to design the processor like this and have it be very efficient. And in fact, it was funny, when we first did the comparison, by the time, if I looked at the time it took for inputs to arrive on the I/O pins of the processor to when the processor woke up, did the computation, and went back to sleep, most commercially available microcontrollers you couldn't even start executing yet because you had to wait for everything to power up. So it just shows you that we had a very different design point as a result of that. And sort of the asynchronous circuits made this very, very easy because there's a very direct relationship between the way our circuits worked and what the application domain really needed at the time. So that was that example. And then on the FPGA domain, this was a research project that sort of happened on pretty much in some ways out of sort of an accident, which is that, as you were saying, my group was designing all these chips, and it's a lot of work to design a chip. And what we said was, why don't we just use FPGAs like everybody else does, right? So you don't have to design the chip. You can use an FPGA instead, and maybe it's not as good, but at least you can sort of do a proof of concept design. And when we looked at that problem, it turns out that because of the way FPGAs were designed commercially, they're designed for synchronous logic. So they're very, very good at that. But it turns out that there's a huge mismatch between the resources available there and the asynchronous domain. So the mapping was really terrible. And like you couldn't learn anything about how good your design was by mapping it to an FPGA.
So mapping a design into the programmable component.
Right. So what we decided to do was build our own FPGA, right? That was more suitable for what we were doing. And that's what we did. And then when we realized that actually having it be asynchronous led to a number of interesting speed advantages. And the reason is because the FPGAs were, in fact, even today, FPGAs were slow because it takes the programmability of the FPGA means that the wires are actually much, much worse than you might think because the wires have to be programmable. So there's a lot of circuitry in the way, so it becomes very expensive. And of course, the way you solve this problem in a normal synchronous design is you put pipeline stages and all sorts of things to make the wires faster. But you can't do that because somebody's already given you the design to map to the FPGA. So it's not very easy to add those pipeline stages automatically with software. And in fact, researchers tried to do that and they weren't very successful. Now in the asynchronous domain, it turns out that because the data tells you when it's there, sort of putting pipeline stages is easy. Just do it. Nobody cares because the data will still tell you when it arrives. And so what you can do is you can design an FPGA where all the pipelining is built in. And if the logic is structured in a way that you can exploit the pipelining, then it runs really, really fast. Of course, if your logic isn't, it's not going to run any better. So that's sort of what happened. And so we ended up having FPGAs where we could map things like DSP operations that ran in some cases actually over a gigahertz throughput on an FPGA, which is sort of unheard of.
At the time, that was a very, very high frequency compared to what you could do in the synchronous domain, right? It was hundreds of megahertz in the synchronous domain.
Right. I mean, I talked to somebody who was an expert at a company who was basically hand optimizing their filters, the DSP blocks to run on commercial FPGAs. And I gave a talk at this company, and he came up to me afterwards, and he was very upset because, and I showed him, we could get gigahertz kind of performance, and he said, he was running at 1/5 that throughput. And he was doing the full design manually, which is an enormous amount of effort.
Optimizing to the nth degree.
And everything, right? It was, it took him 2 years to do this. And, here we could do this in, 5 minutes by using sort of, and he was he was very nice about it, but it was clearly a shock. So that was basically the idea there, that you could actually run a lot faster because of this inherent data-driven nature of asynchronous logic.
So in terms of snap, it was really a power advantage, energy advantage, right? It was more energy efficient. In terms of the FPGA, it was really, there's a speed advantage.
Right, throughput.
The throughput, I should say, throughput.
Yeah, exactly.
But still, we have commercial systems, microprocessors, which are synchronous, right? So people are wondering, this asynchronous sounds so advantageous. Why aren't the commercial manufacturers embracing asynchronous design? Why are they still using synchronous logic?
Well, so there are a number of answers to that question, right? So I think in the microprocessor domain, there are the things that are slowing down microprocessors right now are things I would argue are things like the memory system. It's the organization of the microprocessor, right? So, so because of that, that's sort of fundamental thing that has nothing to do with whether it's asynchronous or not, right? I have to get memory from my memory data from my memory chip to my CPU, and if that's the limiter, that's going to stay the limiter, right? So today, I would argue that for something like mainstream microprocessors, there isn't a huge amount left to squeeze to improve the performance without doing something radically different, right? And industry doesn't like radically different, right? I mean, that which is why a startup company can even exist, right? So that's the challenge, especially given we have all this software installed base. It's not so easy to change. For good reason, industry doesn't like radical changes. I mean, there's a very good reason for that. Makes a lot of sense. I mean, if I would argue, the other thing is sort of asynchronous design. We really didn't know how to do a great job until not too long ago. So I mean, in the 80s, it was the first asynchronous microprocessor was designed in 1988, right? Which is, I don't know, depending on how you want to count, 20 years after sort of approximately the first synchronous microprocessor, right? Something in that order, right? And so when people were sort of, I think in the early stages where it would have been easy to show the advantage, the asynchronous design community wasn't ready. And today, I mean, there's not much left to improve, period. So, I mean, the amount of impact you can show in the microprocessor domain seems limited. Unless you look at it as a very different type of problem, like this, this low power application we looked at for sensing, right? That's a very different architecture. So unless you do something sort of substantially different, if I have to implement, an x86 chip, it's not going to be that much better. I might save some power, but as far as performance is concerned, you've hit diminishing returns a long time ago. We're being limited by lots of other things that are sort of system level problems and not sort of chip level, circuit level problems, I would argue.
So what do you think about the issue? Often people bring up the issue of tools, right? So there's, the companies have this very well developed synchronous tool set, and you guys have developed, a full tool chain for asynchronous design, but there would have to be a huge transition in terms of the design environment in order to move to asynchronous. And like I say, it is risky, and it's and taking these big risks is a little challenging.
Absolutely, and it's I mean, one way I like to think about it is that sort of the synchronous design complexity, the sophistication of the chips you could build, and the design tools that were available, sort of they grew up together, right? So, the tools got better, the chips got better, the tools got better. I mean, there was this nice little, virtuous cycle, if you like, that drove the whole industry, right? For actually, almost 3 decades now? I don't know, depending on how you want to count, right? So it's been a while. And sort of the asynchronous folks weren't ready when this was happening. And so there's actually a big barrier to entry to write good tools. I mean, that said, a lot of the core techniques from a tool perspective aren't that different. But of course, the tools are no longer, sort of all the high quality tools now are produced by industry. And, so we're not in a world where the industry is open sourcing CAD tools. If we were actually, I could produce an asynchronous suite very quickly because I could just reuse a lot of the work they've already done. But in fact, there's a funny story for this. When at my company, we wanted to work with a commercial vendor to map designs to our asynchronous FPGA. And all we did was we basically gave them a new model for performance. We said, don't use what you're using right now to figure out how fast the chip is going to run. Use this other code instead. And it wasn't much code. And they could just plug that into their system and optimize for our chip. With everything else they had done for the synchronous world, just reused, right? So, as I said, if I could get hooks into the commercial tools, I would easily be able to produce a good suite. But that is a barrier right now, and it's sort of a chicken and egg problem, right? A mainstream company isn't going to do this unless some important customer is going to tell them, we want this. The important customer is waiting for the demonstration to say, okay, we need to go in this direction. But to produce that demonstration, you need those tools. So there's this circular dependency, if you like, which was, of course, broken in the 80s in the synchronous domain because designs were small enough that a couple of people could sit down and do them by hand and do a good job, which then could bootstrap this process. But we can't do that anymore. And so that's part of why my group writes some tools, even though we don't write papers about them or we have to do them to get our designs done. But it is an issue. I've talked to a number of companies, and the first thing they want to know is like, who should I buy the tools from? And you don't have an answer to that question. So that's a tough sell. And companies are, the industry is doing okay, right? I mean, companies are making money, they're doing fine. And to compound risk on risk on risk, it's too much. I mean, from a management perspective, I can easily see somebody senior at the company saying, this is crazy, we shouldn't do this. There are too many unknowns. And with good reason, right? I mean, they're on a spec schedule.
So your research group recently collaborated with researchers at IBM to create a chip that you guys call True North, and that the press has been calling the brain chip because it's inspired by the structure of the brain. So I guess if students want to go find this project, they can probably Google brain chip and they'll find it. Now this is not a von Neumann architecture like we're teaching in the course. Can you describe this chip in terms of how it differs from a von Neumann architecture and how it tries to mimic the brain?
Sure. So, I'm not sure I want to get into sort of von Neumann versus not von Neumann because different people interpret that in different ways. But I'll talk about sort of what's the difference between that and sort of a traditional CPU and sort of explain why we designed it that way. So sort of the traditional CPUs today, there's a big bottleneck, right, which is to get data from the memory to the processor and back. So that's sort of everybody calls that the von Neumann bottleneck, right? So because originally that was sort of the idea of the stored program computer, you put everything in memory and then you operate on it. Of course, if you look at a CPU today, it's gone well beyond that. So with lots of parallel cores and so on and so forth. But that's the basic idea. Now, the problem is the cost in terms of both energy and performance. A lot of the cost we're paying today has to do with moving data around and storing it in this memory and moving it from the memory, getting it to the CPU to start doing the operations and then moving back. I mean, the computation itself has become essentially free relative to the communication costs. Right? That's where we are today.
And when you say cost in terms of, for instance, energy?
Energy is the metric I normally, when I say cost right now, I'll pretty much be referring to energy primarily. Right? Because energy has become sort of the first order limiter of the system. So moving sort of data back and forth is very, very expensive from an energy standpoint. Now, so before I say anything, I'll tell you that no one really knows how the brain computes, right? So, however, neuroscientists have various hypotheses. And so the way I like to think about the chip we built is we basically implemented something that corresponds roughly to what a lot of computational neuroscientists think is happening in the brain. So what does that look like? So what it looks like is, our brain has neurons and synapses that are connected in very complicated ways. Right? So, and the other part of this is that the way things, so a neuron, depending on who you ask, can be viewed as a very simple device. One way to think about a neuron is it's got a bunch of inputs. Those inputs, the inputs that arrive on all the inputs that arrive sort of update the internal state, normally sort of adding or subtracting from a value that's stored locally. And then once that state exceeds a threshold, it produces an output. Right? And that's referred to as a spike normally. And this spike is then sent to a number of other neurons, and then the similar sort of operations keep going. Right? So that's how the computation proceeds. So what's interesting about this model is all the neurons are parallel. Right? So everything is inherently parallel. Right? There's no explicit memory like the von Neumann model, but there's implicit state. Every neuron has a little bit of local memory, if you want to think of it that way. So there's implicit local state. And it's all parallel. Everybody's accessing the local state. And the only way sort of state information is exchanged is through these spikes, right? Which you can think of as messages from one part of the system to the other. So that's essentially how the whole system works. So sort of everything is very naturally parallel. Everything is running at actually a very low frequency, right? So timescales that people care about are typically in the millisecond regime rather than the nano or picosecond regime. And so things are slow, and but there's a massive amount of concurrency. Right? That's sort of what the system looks like. And so that's why it's very, very different from this notion of a von Neumann architecture where you have this one little CPU or collection of CPUs which are really, really fast, chunking on data, and then the data is moved back and forth from a big memory. right? That's sort of what happens in the font library. So that's why it's so different. And so what we ended up building in True North essentially is something that can execute this sort of very parallel collection of neurons and synapses and connections.
So there's this very low frequency. I mean, each of these are not clocked by a global clock, right? There's this kind of very low frequency 1 kilohertz clock that runs, and then in between these very long cycles, everything is event-driven and asynchronous. So it uses your asynchronous design techniques.
Yeah, in fact, actually, one of the nice things about the funny things about this project is actually we used the design tools I wrote to design the chip. So you can imagine how hard it was to convince a major company to do that. But anyway, that's a long story. But at the end of the day, yeah, so that's how it essentially works. So there's this one, so the way True North works is there's this 1 kilohertz sort of tick. That's sort of the biological time scale of a millisecond, right? And the reason we have this tick is that there are a number of reasons. One of them is it actually makes it very, very easy for us to ensure consistency between the chip and the software model for the chip, which means that we could have people start mapping applications to the chip before the chip was designed, right? So that was nice. The other thing is when a spike goes from a neuron to another neuron, I mean, it goes through these axons and dendrites and synapses and so on and so forth, and there's a delay, there's a latency. And for certain applications, that the latency really matters. It's used for computation. And so our True North actually allows you to have a programmable delay on a communication link. And that programmable delay is also controlled by this tick, right? So you could have 1 millisecond delivery, 2 milliseconds delivery, 3 millisecond delivery, so on and so forth. That is the granularity at which the delays are supported. So that's the other reason for that tick. But between ticks, everything is asynchronous. The spikes are communicated across the chip asynchronously. The neuron updates are also sort of self-asynchronous. Everything's happening asynchronously until the next tick. So essentially, tick shows up, spikes get delivered at that time. The spikes for that tick get delivered to the neurons on the chip, and then all the neurons update their states and send messages if they need to, so on and so forth. All of that's asynchronous until the next set of spikes get delivered. Right. So normally, if you look at the way True North runs, there's usually a burst of activity and then a lot of waiting for the next tick.
Now, from the numbers I've seen from your papers, so the chip can achieve several orders of magnitude better power efficiency than a conventional design for certain applications.
Right.
So what are the particular applications that this chip is really good at?
Right. So the main thing this chip is good at is, I would say, is the task of just the general task of classification. So classification is actually a pretty broad problem. So what do I mean by classification? So, for example, we're looking at a movie, and you want to know, is there a car in this movie, in the video I'm just watching? Is there a car? Where is it? Or, is there a person walking on the street? Where are they in this image? Right. So that's the sort of tasks that we sort of design True North for. Part of that is because our visual system does this very, very well, right? We still don't know how we still don't know how we do what we do, right? So and doing that sort of in a conventional sort of computer vision algorithm is very computationally expensive. In fact, when you take a picture of something on your smartphone and you do image processing on it, there are many cases where that actually just gets sent to the cloud for processing because there isn't enough battery or on your smartphone or even compute capability to do it in a reasonable amount of time. And so the idea was, we would pick the domains where we know that traditional compute has challenges, and this was probably a domain that we picked for True North.
So where do you, in the future, looking forward, if you develop these systems further, where do you expect to see them appear? Where do we expect that? Will we find them in the cloud to do certain types of problems, or do we expect them in image recognition systems, or
right?
Where would we see these chips in the future?
I think there are a lot of places where, well, first of all, I should say that this is like the first step. I mean, there's a lot more you could do in this domain and do a better job than what we did even with True North. Even though the numbers look really good, a lot of that's coming from architecture, the overall system organization, and we can do even better. So there could be improvements on that before it ends up, being commercially successful. But on the commercial front, I can imagine a number of different domains. I mean, smartphones are a great example. there are plenty of things where you take a photograph and it sort of, tells you various things about the image you've taken. Those aren't that efficient. You could imagine doing that actually on your smartphone. And maybe that's not that important in the US because, we've been spoiled and, we have 4G, high bandwidth connectivity almost at all time. But imagine you're in a part of the world where you don't have broadband where you are, right? Right now, none of these applications are accessible to them, but they would be if we had this on the phone itself. And then another way to look at this is if I look at sort of data centers, for example. I mean, a lot of the sort of the processing of images and things like that is done in the cloud today, but the data centers actually use a huge amount of energy, right? I mean, the data centers are like a small city, right? So that's sort of the statistic everybody likes to use. But there's an opportunity here, today there are data centers that have GPUs built into them for acceleration of certain kinds of operations because people are getting very, very good at using GPUs to speed up a number of different applications. You could imagine these being similar. You could have sort of the neuromorphic or true north sort of brain-inspired architectures sitting as co-processors, just like GPUs are sitting in a data center even. And when you upload your picture with Instagram or your favorite photo sharing application, when you upload it to the cloud, the processing could be done with that for much, much less energy. The motivation there isn't really performance. You can throw as many CPUs as you want, but your power bill might be significantly lower if you used these sorts of chips than just generic CPUs. So that's an application where you do it for power, not because you don't know how to do you can still solve the problem. It just would be more efficient.
Right. You need a lot more resources to do this conventionally, and like you say, power is very, very important. Very, very high cost in a data center. So
exactly.
You can do this much more
most
efficient.
of the cost of the data center now is your power bill, I believe, right? I don't know if it's, yeah. But one of the funny things about True North, somebody asked me about this when I was giving a talk about it, is that they were like, so where's your cooling for this chip? Because everybody sees GPUs and CPUs with these big heat sinks and fins, right? But that's because they're just, those GPUs are dissipating 200 watts or 100 something watts, depending on which one you look at. And True North dissipates 70 milliwatts. So, you don't need a heatsink. But, it's funny because people are so used to, image processing, you're going to need lots of CPU and lots of compute and lots of heat's going to get generated. But actually, it doesn't have to be that way.
Right. So this would actually make it, because of that low power, you could integrate within a smartphone, within that form factor, not worry about the heat dissipation,
exactly.
Battery life because of lower energy.
Exactly. That's the idea. And in fact, today I would argue that sort of cameras have become the new sensor, right? We all have one on our phones. I mean, and because of that, they're incredibly cheap and very high quality, actually. And so anything I can see, in principle, I should be able to extract from an image, right? So, I'm having this conversation with somebody who's interested in smart parking, right? So you want to know how many cars are parked in the parking garage. And everybody's trying to, you can build these nice sensors so that when a car goes over it, it knows that the car has entered a parking space and so on and so forth. But, it's just cheaper if you could take the video feed from the security camera and count the cars. Right? They're already there, the cameras. So, so there's the very interesting things where, there's a much simpler solution to, counting cars, but it's special purpose. Whereas the camera's already there, and anything you can see, if you can do with it, then you'd be in a very different place. So that's another reason why I think these chips are interesting, because cameras are just ubiquitous now.
So what forthcoming trends do you see in the field and challenges that are facing designers of these very, very complex SoCs that we see in our smartphones and tablets and other applications?
So, I think what's happening is, so I'll say in the 90s, we got very comfortable. And what do I mean by that? I mean that, progress in sort of the fundamental manufacturing technology and devices and so on and so forth was just, giving us performance. It's like everything got better. It's amazing. Like, it's, normally when you design something, you can't make everything better. You pick some subset of things that you make better and other things are not as good. That's just the way life is because, the previous design was also done by smart people. Right? But with manufacturing technology, we had this amazing run where not only could you get more complex designs, they could be lower power, they would also be faster and amazingly enough cheaper to manufacture, right? Astounding. It's sort of driven the semiconductor industry for decades, right? I mean, it's astounding. But that's coming to an end, and everybody has recognized this. And so, unfortunately, because this trend was there for so many years, we all got very comfortable because, we had to just do sort of the obvious thing and things got better. But now I think so I think part of it is now we need to sort of wake up again in some ways, right? So we sort of you've got to get people excited again about doing design because I think there's a huge opportunity to do new things, right? Because now finally people are receptive. If I were at a major company, I would say, why bother? There's a risk here. I mean, this is a predictable path. I can do better. But now that's no longer the case. So I think there's an opportunity. I think there are a lot of challenges though, because the thing that we've been spoiled so far is we managed to make microprocessors really, really good. And what's nice about that is the general purpose. We know what we can do anything with microprocessors, right? And there's this nice decoupling between the design of the processor and software. And there's this nice, ISA contract, instruction set architecture contract. I mean, this is very, very clean, and everybody can make improvements and make contributions. But now we're seeing, if to change the underlying architecture dramatically, like even an SoC is actually, I would argue, a dramatic change. It's very, very hard to take advantage of the hardware at the software level, right? So I think that's actually I think we need to go back to a world where both the hardware designers and the people writing software work closer together. But we're sort of not used to that because there was this very clean separation and we all went our separate ways. In fact, it's funny now, it's like people almost don't even speak the same language. And so I think that's a big challenge that we're facing, that we need more people who can bridge that gap because that's where the benefits have to come from. Because we can't just rely on doing nothing at one level of abstract, the software level and seeing improvement. Those days are over. So I think that's a big challenge, and we don't know what to do about it right now. And people are talking about lots of different techniques, but the embedded systems community, which has been around for a very long time, I mean, I would argue that they haven't solved this problem, right? They've been grappling with this problem because they build these sophisticated devices that are all very specialized, and you have this block that does image compression, and this block that there's a processor, but then there's image compression. There might be cryptography, there might be video processing, all sorts of things in a single chip, and you have to sort of hand craft your application to exploit all of these features, and that's very time consuming. There's a reason we don't get a new phone every 6 months. I mean, an upgrade to all the hardware in the phone. It's a lot of work to map things to an architecture that looks like that, and that's where we are today. I think we need to sort of move away from that and get back to a world where sort of the software can be decoupled from the hardware, but have some sort of contract so that you can exploit the features of an SoC. So if I'm a hardware designer and I say, hey, I have this great idea, I could do, I don't know, image recognition this new way, way more efficient from a hardware and power perspective, and I put this block down, well, it should now be used automatically. We don't know how to do that. Whereas, in a microprocessor, I add more, ALUs and
everything just automatically gets faster without the software having to do anything.
It's amazing, right? It's a wonderful place to be, and it would be great if we were back there in the new world. And I think that's a very difficult question, and I think a lot of people are working on it. But it's a hard problem. But I think that's probably the biggest challenge, is getting to a place where we can once again write once again write technology and get improvements in performance without having to, say it takes, 10 years to rewrite some piece of software.
Professor Rajat Manohar from Cornell University. Rajat, thanks for joining us today.
Thanks very much, Dave.